Dear students, in the last class, you have studied about the chemical bonding and the types of bonds, and also you have studied the ionic bond and how the ionic bond is formed and what are the various properties of ionic compounds. And today, let us start from the factors favoring the formation of ionic compounds, or it is also called conditions for the formation of ionic compounds. The formation and the stability of the ionic compounds depend on how easily the ions constituting the ionic compound are formed. It depends on the variable factors like the number of valence electrons, ionization energy, electron affinity, and so on. Let us study in detail regarding this. Coming to the first one, number of valence electrons. The atom A, which is converted into cation, should possess 1, 2 or 3 valence electrons, while the atom B, which is converted into anion, that is B minus, should have 5, 6 or 7 valence electrons. If the atom is having 5 valence electrons, it tries to take 3 electrons to attain octet. If it is having 6 valence electrons, it tries to take 2 electrons. Similarly, if the atom is having 7 valence electron, it tries to take 1 electron to attain octet. The ionization energy of the metal atom should be low. As the ionization energy of the metal atom is low, then this metal atom tries to form ion readily. Hence, ionic bond formation becomes more feasible. An atom with low ionization energy easily forms cation. The electron affinity of the non-metal should be high. Since the release of energy is the sign of stability of a system, the atoms with high electron affinity will form the anions quite easily. This favors to form ionic compound readily. The lattice energy, the one more point is, the lattice energy of the ionic compound formed should be high. Now the question arises, what is this lattice energy? The lattice energy is nothing but it is the amount of energy released when 1 mole of an ionic solid or ionic crystal is formed from its gaseous ions. Example, if I take 1 mole of a cation in gaseous state and 1 mole of anion in gaseous state, when these two they combine, results 1 mole of ionic crystal which is in solid state. During this reaction, the amount of energy, whatever it is evolved, that energy is called lattice energy. Higher the value of lattice energy of a crystal, the greater is the ease of its formation. Hence, greater will be the stability of the ionic crystal. To have higher lattice energy, the electrostatic force of attraction between the constituent ions of the ionic compound should be high. So this could be achieved with the following conditions. That is, how to achieve high ionization, how to achieve high lattice energy. For this, the first one is the charge on the cations. The electric charges on the cations should be large. That is, the force of attraction between doubly charged magnesium ion and the doubly charged oxygen ion in magnesium oxide ionic crystal is 4 times greater than that between monovalent sodium ion and chloride ions in sodium chloride crystal. As a result, magnesium oxide is more stable than sodium chloride. So these values are later on, let us discuss. The another one is the distance between the cation and the anion. So that is the ionic radius, the sum of the ionic radius of the cation and anion is called the atomic or ionic size. That is the distance between the two ions. This should be small. This can be achieved when the cation and anion constituting the ionic compound should be small in size. For a given anion, the smaller the radius of the cation, the greater is the strength of ionic bond. Hence, greater is the stability of the ionic crystal. Since sodium ion is smaller than cesium ion, the force of attraction between sodium chloride is more than cesium chloride. As a result, lattice energy of sodium chloride is greater than cesium chloride. Therefore, sodium chloride is more stable than cesium chloride. Similarly, for a given cation, the smaller the radius of anion, the greater is the strength of the ionic bond. Hence, greater is the stability of the ionic crystal. Among sodium fluoride and sodium iodide, sodium fluoride is more stable than sodium iodide. Coming to the another point, that is electronegativity. Difference of A and B should be high. Greater the electronegativity difference between the two, stronger is the ionic bond. The electronegativity difference of 2 or more is necessary for the formation of ionic bond. If the electronegativity difference is less than 2, it results covalent bonding. Since the electronegativity difference between the sodium and chlorine is 2.1, here the electronegativity of sodium is 0.9 and chlorine is 3. So hence the ionic bond, the difference 3 minus 0.9 will be the 2.1. So the sodium chloride results ionic bond. This is a slide that shows the factors that favors the formation of ionic bond, that is low ionization energy, high electron affinity and high lattice energy. So these are the 3 factors. The same thing is given in this slide also. So low ionization enthalpy, high electron affinity and large lattice energy gives a formation of ionic bond. This is a slide that gives the idea. For an ionic compound, the lattice enthalpy is nothing but it is the heat energy released when 1 mole of a solid in its standard state is formed from its ions in the gaseous state. So if you take 1 mole of sodium ion in gaseous state and 1 mole of chloride ion in gaseous state to form 1 mole of sodium chloride in solid state, whatever the energy that is evolved is called lattice energy of sodium chloride. So it is done with experimental results, and also the Hess law is used during the calculation of this lattice enthalpy. This is a slide that shows the lattice energy of various different compounds. For example, if you take sodium fluoride, its lattice energy is 910 kilojoules per mole. Sodium chloride 787 kilojoules per mole. Sodium, what you can say, the bromide, it is 732 kilojoules per mole. By this, we can say sodium fluoride is a stronger ionic compound and sodium bromide is a weaker ionic compound. Sorry, the sodium fluoride, it is having a strong ionic bond. Yes. Now, similarly, if I take sodium, what you can say, the chloride 787 and so the potassium chloride 701 and the cesium chloride. If you consider their stabilities, so the sodium chloride is more stable because more energy is given out. Similarly, among sodium fluoride, sodium bromide and sodium iodide, so sodium fluoride is more stable because more energy is given out during the system. If I take sodium chloride and magnesium oxide, sodium chloride lattice energy is 787 kilojoules per mole. Magnesium oxide is 3795 kilojoules per mole. These two shows that magnesium oxide is more stable than sodium chloride because more energy is given out. Similarly, among magnesium oxide and calcium oxide, magnesium oxide is more stable than calcium oxide. So, these things can be generally understood with the help of lattice energy. Now, the formation of an ionic bond involves decrease in energy. So, this is a statement. Always the ionic bond is formed by decrease in energy. Decrease in energy means energy is given out from the system so that the formed compound is having lesser energy. So this we have to substantiate with the help of an example, formation of sodium chloride. Now the formation of sodium chloride follows the following steps. In the first step, sodium is in solid state. It absorbs 108.81 kilojoules per mole energy and forms 1 mole of sodium in gaseous state. This we call it as enthalpy of sublimation and the reaction is endothermic. Now in the second stage, the dissociation, the chlorine, it exists in molecular form. This molecule, it breaks or it dissociates to form atoms. So the energy that is required to break 1 mole of chlorine to form 2 chlorine atoms is called enthalpy of dissociation. But during the formation of sodium chloride, we need only 1 chlorine atom. Therefore, half a chlorine molecule undergoes dissociation to form chlorine atom in gaseous state. That dissociation energy is 121.35 kilojoules per mole and this reaction is also endothermic reaction. The third step is the conversion of sodium in gaseous state to form sodium ion. So this can be achieved by supplying the energy. That energy we call it as ionization energy. When we supply 495.8 kilojoules per mole of the energy to the 1 mole of sodium in gaseous state, it forms 1 mole of sodium ions in gaseous state and gives 1 mole of electrons. And this reaction is endothermic reaction. Later on, the electron is added to the chlorine atom which is in gaseous state, forms chloride ion and this we call it as electron gain enthalpy. During this electron gain enthalpy, the reaction is exothermic. The energy is released during this reaction. Finally, the sodium ion in gaseous state and chloride ion in gaseous state, both are in 1 mole. They combine to form 1 mole of sodium chloride in solid state. During this reaction, the energy released is 769.2 kilojoules per mole. And this energy is called lattice energy, and the reaction is exothermic reaction. Now, the overall reaction, what it is taking place, that is the total energy absorbed, is nothing but it is enthalpy of sublimation plus half the dissociation energy plus the ionization potential. If you add all the three, we get 725.96 kilojoules. And the total energy released is nothing but electron gain enthalpy and lattice energy, both the summation of these two. So that gives the 1117.9 kilojoules, that is 1117.9 kilojoules. If you take the difference here, it shows energy released is more than the energy absorbed. So the overall in this reaction, energy is released. That energy released is 391.94 kilojoules. This is called standard enthalpy of formation. So this illustration tells that formation of ionic bond results decrease in energy. Now coming to the another point known as hydration of ions or solvation of ions. The word hydration is used for the water, and in general it is called solvation using any type of the solvent. The solubility of ionic solids in water is mainly due to the polarity of water molecules. We know that the water is a polar molecule because oxygen is more electronegative than hydrogen. As a result, on the hydrogen you have a partial positive charge, and on the oxygen you have a partial negative charge. Now the positive end of the water interacts with the negative end ions of the ionic solids, and the negative end of water interacts with the positive ion of the ionic solids, and this process is called solvation. In general, for water it is called hydration. It is represented as the positive, the cation M. It is solvated with the water where the oxygen is nearer to the metal ion and hydrogen part is away from the metal ion. And it results XH2OY, that is the negative ion, is surrounded with the water molecule where hydrogen part is nearer to the negative ion and oxygen part is away from this. The attraction of positive and negative ions of an ionic compound towards the water molecules, resulting in the dissolution of an ionic solid, is called hydration. For any other solvents, if you use, in general it is called solvation. The process by which the solvated or hydrated ions are produced is called solvation or hydration process. The process of solvation is accompanied by release of certain amount of energy. This energy is called solvation energy, or in case of water it is called hydration energy. And this hydration energy or the solvation energy can be represented in this slide. If you take a gaseous ion, when you add a solvent to this, the ion gets solvated and energy is released during this. That energy is called solvation energy. In case of water, if you use that energy, we call it as hydration energy. This is a slide that I have shown. There, the sodium chloride. So, in this sodium chloride, so oxygen is having the more polar and hydrogen is having a positive pole. So hydrogen is nearer to the sodium, the chloride ion, and oxygen is nearer to the chloride, the sodium ions. So this is how the solvation takes place. This slide shows about the solvation, lattice energy and hydration energy in case of the sodium chloride. So the energy released when 1 mole of ion are brought together from infinite distance, we call it as lattice energy, and energy released when 1 mole of ions undergo hydration is called hydration energy. Solvation energy is also called heat of solvation or heat of hydration, which is always an exothermic process. Then how to define this? The amount of energy released when 1 mole of gaseous ion is dissolved in a solvent is called solvation energy, and in case of water it is called hydration energy. This solvation energy and lattice energy both are responsible for the solubility of the ionic solids. So the solubility of ionic solids in water depends on solvation energy and lattice energy. Ionic solids dissolves in water when hydration energy is greater than lattice energy. Students, this is very important. So, the ionic solid dissolves in water when hydration energy is greater than lattice energy. The ionic solid is not going to dissolve in water when the hydration energy is less than lattice energy or lattice energy is greater than hydration energy. The example, sodium chloride is soluble in water because its hydration energy is greater than lattice energy. Whereas the same silver chloride is insoluble in water, it is because its lattice energy is greater than its hydration energy. Now the question arises how to calculate this lattice energy. The lattice energy can be calculated in two ways. One is based on the theoretical equation given by Born and Lande, and another by Born and Haber through the experimental results. Now, the following equation is called Born-Lande equation for the calculation of lattice energy. This is the theoretical equation, so which also gives good results for the calculation of the lattice energy. Born-Lande equation is lattice energy is equal to minus Z plus Z minus, that is atomic number of cation into atomic number of anion into E square, that is E is charge on the of an electron, capital A into N divided by R naught into 1 minus 1 upon N per mole. So A is called Medulin constant, N is the Avogadro's number, R0 is called inter-ionic distance, and small n is known as Born exponent. Now, the Madelung constant A for different crystals are constant values. For sodium chloride, Madelung constant is 1.7476. For cesium chloride, 1.7627. Zinc blende, that is zinc sulfide, 1.6381. And for titanium oxide, which is called the rutile, it is 2.4080. Students, these calculations or these you have to remember in detail. Of such things you are going to learn in what you can say the subsequent classes. Born exponent for different electronic configurations of ions is given. So, if the ion attains the electronic configuration of helium, then the Born exponent value is 5. The ions which attains the electronic configuration of neon, so the Born exponent value is 7. And if they attain argon configuration, Born exponent value is 9. And if they attain krypton configuration, the Born exponent value is 10. There I have given the example. Lithium and beryllium ions, they after losing 1 and 2 electron, they attains the electronic configuration of helium. So the N value will be 5 here. In case of sodium ion, magnesium ion, oxide ion and fluoride ion, they attains the configuration of neon. So the value is 7. Based on this, let us take a problem. Students, in the examination, the problems will be asked based on this. Let us take the first problem. Calculate the lattice energy of sodium chloride crystal with the help of Born-Lande equation. So the equation is given here for sodium chloride. So the sodium ion charge is 1. Chloride ion charge is also 1. Therefore, Z plus is equal to Z minus, that is equal to 1. So the charge on the electron is 4.8 into 10 raised to minus 10 ESU. For sodium chloride, the Madelung constant A is equal to 1.7476. So the N is the Avogadro's number and R0 is the radius, the distance between the two ions. So here the radius of sodium ion is 0.95 and radius of chloride ion is 1.81. So sum of these two will be 2.76 angstrom or 2.76 into 10 raised to 8 centimeter. Now the Born exponent for this, that is N is equal to, for sodium, Born exponent value is 7. For chloride ion, it is 9. 7 plus 9 divided by 2 will be 8. Now, if you substitute these values in the Born-Lande equation, so at the end you get lattice energy of sodium chloride is 184.03 kilocalories per mole, and this value is in very close agreement with the value calculated from experimental results. There is another method to calculate the lattice energy experimentally, and this we call it as Born-Haber cycle. The lattice energy of an ionic solid can be determined experimentally by a process known as Born-Haber cycle, devised by Born and Haber in 1919. The determination of lattice energy of sodium chloride by this cycle is based on the fact that the formation of 1 mole of crystalline sodium chloride can occur by the following two processes. In the process 1, the following two processes. In the process 1, in this process, 1 mole of solid sodium combines with half mole of chlorine gas to form 1 mole of crystalline sodium chloride. The process is exothermic and the heat evolved during the process is called enthalpy of formation of sodium chloride. That is, the reaction is sodium solid combines with half chlorine gas, means 1 chlorine atom, to form sodium chloride solid, and the energy evolved is Q kilojoules, and this energy is called enthalpy of formation. The same reaction takes place in the following steps, that is in the process 2. So in this, it contains the following stages. The first stage is conversion of solid sodium to gaseous sodium atom. So during this, the heat energy is absorbed, and that we call it as plus S kilojoules, which is nothing but enthalpy of sublimation. In the second stage, sodium gas converts to sodium ion in gaseous state, and this we call it as enthalpy of ionization, which is also endothermic. The third stage is the conversion of the chlorine molecule into the chlorine atom. Here, half chlorine molecule turns to 1 chlorine atom, and the enthalpy of dissociation value will be half D. The fourth stage is the chlorine in gaseous state. The atom takes an electron and forms chloride ion in gaseous state, and this we call it as electron gain enthalpy. This electron gain enthalpy is an exothermic reaction. Lastly, both the sodium ion in gaseous state and chloride ion in gaseous state combine to form 1 mole of sodium chloride in solid state, and energy released during the process is called lattice energy. So, by the Hess law of constant heat summation, so the total energy, that is enthalpy of formation, is equal to the summation of all these the energies. That is, enthalpy of formation is nothing but it is enthalpy of sublimation plus enthalpy of ionization potential plus half the enthalpy of dissociation plus enthalpy of electron gain enthalpy, and the lastly the lattice energy. The same thing is shown in the diagrammatic way, or it is shown in the form of a cycle. This cycle is called Born-Haber cycle. Students, go through this Born-Haber cycle and try to practice to write it. Based on this, the problems also will be asked. So the first one, calculate the lattice energy of sodium chloride crystal from the following data. So the data are given there. So the enthalpy of formation is given, enthalpy of dissociation is given, ionization potential is given, electron gain enthalpy is given, so enthalpy of sublimation is given. So based on this, substitute the values, and the lattice energy for this will be minus 759.7 kilojoules. Like this, students, go through the problem 2 and problem 3 to calculate the similar way. This slide shows once again the Born-Haber cycle, how we can write the Born-Haber cycle. In this cycle also it shows the sodium solid turns into the sodium gas, and the amount, that is energy absorbed, is enthalpy of sublimation. Sodium gas turns to sodium ion in gaseous state. That energy is 496 kilojoules. It is enthalpy of ionization energy. Half chlorine molecule turns to chlorine atom in gaseous state. It is enthalpy of dissociation, and the value will be half. It is actually for 1 mole, it is 244 kilojoules. for half mole it is 122 kilojoules. This chlorine atom in gaseous state turns into the chloride ion by accepting an electron, and during this reaction energy is evolved, that is 349 kilojoules of energy is evolved. So therefore, we have enthalpy of electron gain. And these ions in gaseous state, they combine to form sodium chloride solid, and the energy evolved is called lattice energy, which is 788 kilojoules. So by the Born-Haber cycle, the following equation, that is enthalpy of formation is equal to summation of enthalpy of sublimation, ionization enthalpy, dissociation enthalpy, electron gain enthalpy, and lattice energy. This is the another way of representation of the Born-Haber cycle. In this, the starts from this position. So here the sodium solid combines with half chlorine gas and results sodium chloride. The process 1 is this. This is the process 1, and the rest of the top and bottom, that becomes the processes 2. Now in this, coming to in the second stage, in the second stage, the first process, sodium solid turns to sodium gas. This process is the enthalpy of sublimation. The next is the sodium gas turns into the sodium ion. Here also the enthalpy of ionization, and third. So all these upward arrow marks, energy is absorbed. This is all endothermic reaction, and here enthalpy of the electron gain and the lattice energy. So these are all the energy evolved during the reaction. So this is what you have to remember regarding the what energy is evolved and what energy is the absorbed. So total of this in the form of like this. So this becomes the what you can say the Born-Haber cycle. In another way you can represent it. Now coming to the next. This is a diagram. It shows the formation of cesium fluoride. In this cesium fluoride, how cesium fluoride is formed and the Born-Haber cycle related to the formation of cesium chloride is shown. Students, go through this table and try to explain about the formation of cesium fluoride. Similarly, here this is the Born-Haber cycle for calcium fluoride. So in the formation of calcium fluoride, now the calcium gives 2 electrons and 2 fluorine atom takes 1 electron each and forms calcium fluoride. And the lattice energy in this reaction is much higher compared to this. So here also, so it is shown the calcium turned into the calcium ion in gaseous state, energy absorbed, and in this case also it turns into the gaseous ions, so energy absorbed, and in this case the fluorine gas turns into the undergoes a dissociation to form the fluorine atoms, the endothermic reaction, and subsequently this reaction is electron gain enthalpy. The value is because 2 into minus 327.9 kilojoules. And finally, it forms the calcium fluoride. So this is how the Born-Haber cycle you must able to draw for this. Now This is a Born-Haber cycle for magnesium oxide. This is the Born-Haber cycle for sodium nitride. And finally, this is the Born-Haber cycle for zirconium oxide. Students, you must able to draw these Born-Haber cycles for different compounds. So this much what you have to learn regarding the Born-Haber cycle for the various ionic compounds. Students, this is about you have to learn about the ionic compounds. Go through this, and if you have any doubts, so you can ask in the class. Thank you.